Hello, everyone. We are happy to have Surjeet here to give us the tutorial for his own lectures. And yeah, Surjeet, over to you.
Great, sure. Okay, yeah, I guess someone is live streaming the thing. That's fine too, no problem. Okay, so yeah, so I'm perfectly happy to be guided by you guys in terms of what you're interested in knowing more about for these tutorials. It's really just for your benefit. I don't know how shy people feel. If so, maybe I'll give the opportunity first. Is there, if someone wants me to go over some of the material more carefully, more slowly, obviously my talk was very rapid. So let me first ask if there's anything someone is curious about, to want to know more about. I can start with those topics. Otherwise, I'll just simply overview things again. So let me give you the opportunity to the audience. Is there anything you guys are curious about, want to know more about? And I'm happy to talk about anything, really, not just specific things I've discussed in the last few lectures, but any aspect of phenomenology, things of that sort.
Yeah, I think the participants can unmute themselves, or maybe they can raise their hands, and then I can unmute them if they have any questions.
Okay, I mean, looks like people are somewhat shy. All right, so overall, right, like the main topic that I discussed was detection of dark matter. And for me, right, the main question has been, given that the range of dark matter is enormous, something like the mass of dark matter is less than or equal to 10 to the 48 GeV, and it's greater than or equal to something like 10 to the negative 22 electron volts, right? That's an enormous range of masses. And so far, what we have as a community been doing is just focus on two specific candidates, right? We have focused on WIMP dark matter, which is like something like a mass of 100 GeV, and one kind of axion, which is an axion with a mass of around a gigahertz or so, right? And both of these are essentially driven by sort of theory motivations. WIMPs because WIMPs naturally sat within supersymmetry, and this kind of axion because people put various cosmological limits, things of this kind on that. And we've been looking at it for like 30 to 40 years and we haven't found it. So for me, the main point has been the fact that, look, if you're asking a question about what is there in the natural world, right? What is dark matter? What is this particle? You're not going to solve this problem from the armchair, right? Physics is an experimental field. And as much as you would like it to be the case that you think you can sit in an armchair and figure it out mathematically, it's not going to work, right? You got to go out there and see what's actually in the world. So the real question is, when it's a funny human tendency. You see this huge part of parameter space, right? It's something like whatever, 60 orders of magnitude sitting in there. And people decide that the right thing to do is to somehow come up with theory motivations for why you should look at a small part of parameter space because it is theoretically well motivated. And for me, that has always been silly, because the reality is that we don't know. It could be anywhere in here. And so the correct thing to do is to parameterize how one can experimentally make progress, right? The answer is not to come up with theory arguments for why dark matter is in this very narrow range. That's a bit silly, right? How do you know what particles are out in the world? You have to go look. So the correct response, in my opinion, is how do you parameterize an experimental search program, really, an experimental program that can search over this entire swath of parameter space. That has been my take on this problem for a long time. Okay. So that was exactly what we were trying to do in our work. Okay. So, and one of the things about physics is that even though this looks like a very, very broad range of possibilities, what we can in fact do is parameterize it in a sensible way using just like quantum field theory techniques, right? So we can say, even though the range is very broad, right? The right way to do it is to say, what are ways in QFT that allow us to detect a new particle. So maybe that's a poorly spelled out sentence. What I really mean is QFT, quantum field theory, restricts the kinds of interactions your dark matter could have with the standard model. And that is being the governing idea in many of these experiments. And what we said is that if the dark matter is extremely light, right, ultralight dark matter, there are only like 7 possible interactions an ultralight dark matter particle could have with the standard model. And we parameterize them basically by saying if it's a scalar, a spin 0 interaction, right? The kinds of operators I can write down is essentially A F of dual, A GG dual, D mu A, psi bar, gamma mu, gamma phi psi, and then a coupling to the Higgs of the form GA Higgs squared, where A is my new field, right? And then you can say if it's spin 1, and I still want it to be technically natural and light, things of that kind, I basically write this as the possibility that the new dark matter field F prime, mu nu, can talk to standard model fermions through a dipole operator, psi, I guess, again. The kinetic mixing, epsilon, F prime F. And finally, there could be a direct charge in the standard model, which is some G, J mu, and the new gauge boson, A mu prime. That's it. So we're just doing an operator analysis, right? It says, I don't really care where the dark matter comes from, what it's going to be produced, none of that stuff. I'm not coming up with theory motivations for X, Y, and Z. I'm just saying, if there is such a field, that the field is very light, that is the lowest mass end of it, these are all the interactions I can actually write down. And strangely, for 30 years, people were only focusing on one interaction. They're talking about axions produce coupling to photons. That's pretty much what people were looking for 30 years. And my point was, why do that? You can look for all of these other things. These are also equally legitimate ways in which the dark matter can talk to us. And let's come up with experimental methods to probe it. And that is largely what we've been doing. So to some extent, even though I sort of bashed a little bit of theory in the beginning and said, look, this is an experimental question. It is an experimental question, but at the end of the day, there is a theoretically good way to make progress by just sort of picking what we need to do. Okay, so that was the motivation. So are there questions about this or anything specific you want me to go over in more detail?
Maybe, maybe I'll just start off with one question. One broad question about the various things that you're saying. So most of the things that you described in your lectures, both for the light and the heavy dark matter, most of them were terrestrial experiments with some astrophysical things thrown in and so on. So, what do you think about generally cosmological, experiments or even things which are, about early universe in general, so generally, I mean, some of these axion things, I know people have looked at such kind of thing, but or even large scale structure, for example. But like these other couplings, could they be probed by such kind of experiments?
Yeah, actually, good. So, if you think about anything cosmological, right? So the key issue with anything cosmological is the fact that we don't have precision. You have to look at what the cosmology is giving you. And so let's look at it in terms of, no matter what, whether you're doing a terrestrial experiment or an astrophysical experiment, the operators you have in mind are only these, right? Because that's just restricted by quantum field theory. So if it's anything cosmological, the main thing is that, you have to ask, what is the probe particle that can go from far away towards us? And the probe particle that cosmologically can go from whatever cosmology is happening to where we are is, of course, electromagnetism. Right? Because if you have a fermion, okay, it's true, we get cosmic rays from far away, but fermion spins, which is what this operator controls, is not something that we can control very well, right? Because that gets shifted by magnetic fields. And remember, we're looking for dark matter, so these effects are extremely small. So with anything else, whether it is the fermion spin, things of that kind, we don't have pure astrophysical objects. So what we can do really is just look at photons. And that is one of the reasons why most of the experiments that are more cosmological in nature. So people look, for example, at the rotation of the polarization of light. So let's talk about that briefly. So if you have this coupling AFF dual, one of the things this will actually do is that, let's say you have the CMB, right? The CMB is somewhere here, and we are somewhere here, and the CMB is producing light. So what this will actually do is that if you have this coupling AFF dual, it will actually cause a rotation in the polarization of light. Okay, so of course, the polarization of light is like spin, obviously. So if you send light that is entirely E mode polarized, when it actually arrives on the ground here, some of that E mode will actually become B mode. Now, the reason why this is a useful thing to do is because in general, it's very hard to rotate the polarization of light, right? As opposed to a spin, which of course can be rotated by a magnetic field. The polarization of light is much harder to rotate through things of that kind. So people do these measurements. They look for E to B rotation. And in fact, the absence of B mode rotation in the CMB is a limit on certain kinds of dark matter already. One can do that. The other kind of astrophysical thing one can do, and in fact, following our work, people are doing this, is this other coupling to the Higgs, right? So we have this coupling GA Higgs squared. One of the things that this actually leads to, we said, is basically that at low energies, this becomes effectively a coupling of the form, let's say, to the electron mass. There's an MEA, over the Higgs web, basically. There's a G Higgs web denominator, or really M Higgs, sorry. Psi bar psi for electron mass. So what this, of course, leads to at the end of the day is the statement that there will actually be, M squared here, that there will actually be a time variation in the mass of the electron. Okay. So when you have a time variation in the mass of the electron, one can actually look at these sort of pulsar timing arrays. So, so I don't know if you call them really astrophysical measurements or whether they're like local measurements. Of course, the instrument you're using is an instrument on the ground, but you're really looking at a distant astrophysical object. So what will happen in this particular case is that if you have this kind of interaction, what will actually happen is the following. Let's say you're on the ground here, you have a little clock with you. Okay, and there is some distant pulsar here.
Sorry, could I just ask clarification? So the G here is SU2 coupling, or?
No, this is the new interaction with the Higgs itself. So this is a new coupling, it's not SU2.
Yeah. G in general, okay.
Yeah, so G has dimension 1.
Okay.
So G is a tiny number in this case. Right. So what happens is that if you're actually going to have the mass of the electron change, things of that kind, if you have this pulsar, right, this pulsar is emitting light to us at regular frequencies, at regular time intervals. And all you're doing is you're sitting on the ground here and trying to measure the time of arrival of these pulses. And your atomic clock, of course, depends upon the mass of the electron, because it is the mass of the electron that sets the frequency in the atomic clock. Right, it's the binding energy of the electron in the atom that ultimately sets the scale for the clock. So if the mass of the electron keeps fluctuating locally, it keeps changing, even if the pulsar is emitting light to us at regular periods, the time of arrival will keep modulating up and down. And that is basically how you use these pulsar timing arrays to search for this kind of dark matter. And you may call that either a local measurement, because of course, at the end of the day, it does involve a local instrument, but it fundamentally makes use of a distant astrophysical object. So, but again, right, the messenger of this change is happening through light. because light is the only thing that you can actually get from faraway objects that is not getting messed up by things like interplanetary magnetic fields and stuff like that.
So the idea is that the pulsar timing is not affected by any, or at least it's not affected the same way. There's some, like desyncing between there and here. Is that the idea?
Pardon me, what did you say? The pulsar timing is what?
So if the pulsar is also, like oscillating the same way,
Yes.
then
Yes.
like it would not be detectable, right?
Right. So yes, so the pulsar was exactly in sync. But the point is, right, essentially, if you think about it, the pulsar is very, very far from us.
Yeah.
Which means that the phase of this, so first of all, since it's very far from us, the field of the axion on the ground is completely different from what it is over there. Right? Not only that, these things are from some kiloparsecs away, which essentially means that when the light was emitted from this pulsar, the time when it was actually emitted is very different from the time when we're actually measuring it over here.
Right.
So there is no way that the phase of the axion when the light was emitted will be the same as the phase when it's actually being absorbed.
Yeah. Presumably there's also some, like, but if there's some, like if the pulsar is moving with respect to us, right?
Yes.
So you have to correct for that, right?
You do have to correct for that, correct? Absolutely. So what do you actually do in these pulsar timing arrays is essentially this thing that, you kind of look for multiple pulsars, not just one of them. And you're kind of looking for an overall scalar wave. Like essentially, you look at this pulsar and you see what the shift is, this pulsar and you see what the shift is, and so on and so forth. So basically, the main idea here is that you're essentially looking at the fact that the signal is the same in all directions, basically. And notice that what we are fundamentally interested in is not just let's look at the kind of noise that one might have. So one kind of noise is exactly what you're pointing out, which is that the pulsar, if it is actually moving towards us, in general, it has a random velocity, right? That random velocity will give rise to a Doppler shift. And indeed, that Doppler shift is enormous. It is large compared to the signal I'm looking for. So specifically, what I'm looking for is not just a constant change to the axion. I'm actually looking for a time variation. So I'm looking for the fact that this axion field is A naught cosine MT, which means it will oscillate up and down at a frequency equal to the mass of the axion. Okay, so let's say the mass of the axion is 1 Hertz, just for the heck of it, right? Just to give you some time scale. What this means is basically that the signal from the pulsar will have one value for 1 second, and then the next second it will be totally opposite, and then keep changing back and forth, right? So the signal we are looking for is an oscillatory signal. While if there's just a Doppler shift, that is constant in time, right? So that basically means that a Doppler shift will not mimic a signal that is going up and down. Of course, if the pulsar itself is oscillating back and forth at a frequency of 1 Hertz, that will indeed appear like a signal for me. But why would a pulsar itself move back and forth at 1 Hertz? It probably would require a planet or something like that nearby, which is actually causing it to gravitationally wiggle back and forth at 1 Hertz. But 1 Hertz is pretty close, right? Like, so in some sense, the idea is that you don't really have large objects that close to a pulsar in order to make it wobble back and forth at 1 Hertz, because 1 Hertz means the two things have to be at something like a 10,000 kilometer distance from each other. And, in general, that's just not true. So the key thing is that we already know that pulsars are stable clocks. We've already measured it independently of this, which is why we're able to actually look at these very tiny effects in a good way. So that is the main point. The main point is that we're not looking for a DC offset, right? A Doppler shift by itself would basically be something that's constant in time. It just has to do with like a constant velocity. A constant velocity signal is very, very hard to look for experimentally for all these reasons that you mentioned. But something that's oscillatory is fundamentally better.
Okay.
Yeah. is there a way, let me read the chat message there. Is there a way to study dark matter by trying to study the physics of reheating after inflation, but presumably dark matter interacted more with ordinary matter? Well, the point is we have very few signals that we directly get from reheating to us. Some people do talk about the possibility that, depending upon what model of reheating you have and what model of dark matter you have, you might in fact have the possibility of gravitational waves being produced by reheating. Okay. But that again is very model dependent, does not give you a model independent way of measuring on the ground. And it's pretty indirect because it just has to do with how these things actually happen from one place to another. And, so I think that's generally pretty hard to do.
I mean, like, is there, is there any way to bound how complex the dark matter can be? For example, like you're talking about models where there's a whole dark sector with dark nucleus and things like that, big bound state.
Right.
Now, like if something like Big Bang nucleosynthesis had happened, but in the dark sector,
yeah,
like, is there any way that we can say no, that could not have happened, because of these experimental?
Not really, unfortunately, because in a sense, all we know, right, about dark matter is like, actually, yeah, this is an interesting fact. Like, what do we know about dark matter, right? What we know about dark matter is basically, all we know is from the bullet cluster, right? Essentially, we know that in the bullet cluster, I kind of had, what happened to my thing here? I had this cluster and I had this cluster, and these guys went right through. The dark matter went right through. That's pretty much all we know. And that just gives this very weak limit on the interaction cross-section of dark matter with itself. It says the dark matter self-interaction cross-section divided by the mass of the dark matter has to be less than or equal to 10 to the negative 25 centimeters squared per GeV, right? That's an incredibly weak limit. So it's not actually something that is all that constraining. So yeah, it's just true. It's the fact that most of what we know about dark matter is from gravity, and the additional fact that there's only about 5 times more energy density in dark matter than regular matter, which together means that it's very, very difficult to distinguish baryonic effects from the effects of dark matter in general, right? Because it's only a factor of 5. And once you don't have some order 1 interaction like what the bullet cluster is actually looking for, it becomes extremely hard to do any kind of serious probe of it. So unfortunately, that's difficult.
Okay.
Yeah. So I mean, since you guys are string theorists, I just want to know, what are you guys curious about in general about this field, right? That's the thing. Yeah.
I guess different people are curious about different things. So
exactly. That's right. Yeah, I mean, that's more what I meant, like in terms of like, what is it about the dark matter question that interests you? That's kind of more what I was asking. So the other kind of thing I talked about was, of course, like gravitational wave detection, which is a generally interesting area in the sense that, we are, I think, likely to learn very interesting things about the world through gravitational waves. And the general question is basically the issue of what is the technology you need to use to detect gravity waves. And it's a little bit like this, right? If you look at electromagnetism, right, we have lots of different ways of, probing electromagnetism. There are like gamma ray telescopes, through X-ray, optical and radio waves, whatever, all kinds of things. And what you learn is basically that depending upon the frequency of the light, the technology is very different, right? A radio wave is just an antenna. That's all you do. You put some chicken wire and you try to detect the current in the chicken wire. An optical telescope, you build an extremely expensive mirror. For an X-ray telescope, you kind of use, I don't even know what they use. I think it's some kind of CCD style devices, things of that kind, maybe, And for gamma ray detectors, you actually put a particle detector. That's what you literally fly. So what you really are seeing is that depending upon the frequency and energy of the light, the technology is dramatically different, right? frequency tells you what technology you need. And similarly, this is the same thing in gravitational waves as well, right? So in the gravitational wave spectrum, we are basically looking at gravitational waves, let's say roughly from about 1 kilohertz to about 1 nanohertz. And that's about 12 orders of magnitude in frequency there. And so depending upon what frequency you are interested in, the technology you need is quite a bit different. So what we talked about is that like LIGO, for example, uses optical interferometers. I was pushing for, atom interferometers terrestrially from 0.1 hertz to 10 hertz, right? So like LIGO, for example, is above here. And I'm pushing personally for atom interferometers, let's say. So LIGO is, let's say, 100 hertz. Well, let's make it 10 hertz. I don't want people to get mad at me. So 10 hertz, let's make it 10 hertz. And I was saying from 0.1 hertz to 10 hertz, maybe you do atoms. LISA would be from about 0.1 millihertz to 0.1 hertz would be LISA. And there is already an experiment called nanograv or pulsar timing arrays. They already exist. PTAs, let's call them that. Pulsar timing arrays at nanohertz. And there's other stuff that talked about using asteroids and things of that kind. They're trying to fill in this gap here. So you're basically seeing that depending upon what kind of frequency you're looking at, you need different technologies. And for gravitational waves, in large part, the technology is driven by the need to balance precision, which is the fact that you're trying to measure some very, very small effect, with stability, which is the fact that to detect gravitational waves, you have to ensure that whatever it is you're trying to detect the gravity wave with only moves due to gravity and nothing else, right? And it is that balance between these two things that actually tell you what kind of technology one actually needs. So that was sort of the motivation for a lot of what we were thinking about. Of course, the atom stuff that I talked about is much more advanced because that's been going on now for like 12 to 13 years, while a lot of the other things are papers that we're still writing and hoping for people to, sort of get involved and push forward. How successful they will be, I have no idea. But, one has to be optimistic in this game. So was there anything there that you guys had more questions about, were more interested in, or want to know more about? Yeah, someone has a question. Speak up.
Yeah, hi. So I was thinking about the stability thing that you were explaining yesterday, and I couldn't completely understand why. If I'm not wrong, you said that for greater stability, you have to go to like smaller distances. Is that right?
Greater stability. No. So the plot is the following, that essentially you see that if I look, so this is a plot of just astrophysics, okay? This has nothing to do with gravity wave detection. So what you see is that here is the strain of the gravity wave and here is the frequency. What you see from astrophysics is that if you want to detect gravity waves at say nanohertz, okay, there are known sources of gravitational waves at nanohertz, which give you an amplitude h of around 10 to the negative 15 even. While at LIGO frequencies, which is basically more like kilohertz, you require h of around 10 to the minus 23. Okay, so that's an astrophysical plot, right? So this says there are supermassive black holes here and solar mass black holes here. Okay, solar mass black holes here. So what I'm saying is that this is the job you need to solve, right? In a sense, if you want to see gravity waves at kilohertz, you require extreme precision. At nanohertz, that is a signal in amplitude that is about 8 orders of magnitude larger, which means you don't need as much precision, but your challenge is stability, right? In the sense that if I to try to detect a gravity wave, in some sense, what you're doing is you're saying there are two objects, and I'm trying to measure the distance between them, which is fluctuating as L plus HL, right? The separation is L, and I'm causing some gravitational wave going by. It causes the distance to fluctuate by an amount HL. But to do that, I have to make sure that these two guys are not moving by an amount larger than HL by any noise source. So let's just put in some numbers, okay? And let's take this nanohertz as an example. So let's say I take two objects, okay, separate them by 1 astronomical unit. And let's say the amplitude H is about 10 to the minus 15. Okay, so an astronomical unit is about 150 million kilometers, which is about 10 to the 11 meters. All right. So if H is about 10 to the minus 15, that means HL is about 10 to the minus 4 meters. So what this means is that if I, for example, take two objects in the solar system, right, and separate them by 1 astronomical unit, which is a fairly reasonable distance, the distance between them will fluctuate by 10 to the minus 4 meters. That's a pretty large distance change, right, in terms of measurement, right? If I'm trying to measure the distance between two objects, 10 to the minus 4 meters is a pretty big distance compared to modern technology. So in terms of the technology you need to measure that small distance, this is not that challenging. But what is challenging is that how do you take two objects in the solar system, right, and make sure their distance is not changing by more than 10 to the minus 4 meters by all kinds of random noise, right? Basically, solar wind hitting you, solar intensity fluctuations. Because if you look at the sun's intensity, right, every few hours, the intensity fluctuates by 10 to the minus 3. But that's a large intensity fluctuation to operate for such a long time. So what you really care about at low frequency is not the ability to measure a small distance. It is much rather the desire to make sure that these objects are only moving due to gravity and nothing else, right? To put it in perspective, right, at LIGO, you know, they have this 4-kilometer arm and they do a 200 bounces for it. Effectively, 1,000-kilometer baseline is what they have. And they're trying to measure 10 to the minus 23 in strain. So LIGO has to measure a length change delta X order 10 to the minus 18 meters, right? So technologically, that is about 14 orders of magnitude more precision that you need, right? But if you want to be in the business at low frequency, you don't need as much precision. What you need is stability. So it is really a different problem that you're trying to solve. Did that answer your question, or?
Doesn't the same like stability problem happen for like as you wouldn't the stability problem get worse as you go to like lower and lower distances? Because
Lower and lower distance or frequency? What do you mean, distance or frequency?
because okay, it just I was just thinking, like, if you were to measure something at a distance as small as 10 to the power minus 18, wouldn't there be like even more things affecting?
Good. I see what you're saying. Yeah, good. So now comes the issue of how can you do vibration isolation. So let's talk about this, right? So notice, good. So delta X, right, is acceleration times t squared, right? So let's look at this following fact. It's a t squared. So let's look at the distance, the difference between nanohertz and kilohertz in time. Okay. So the same acceleration. So suppose there is some force, right? There's some force. Ultimately, you know, at the end of the day, what you're asking is not a question about distance. What you're asking is how large of a force is acting on something and how bad is it? Okay. So if you fix the amplitude of the acceleration, what you notice is that the same acceleration, amplitude of acceleration at a low frequency would correspond to a much larger length change than at a much higher frequency, right? Because the time notice is going to go as 1 over the frequency, right? Which means for a fixed acceleration, the amplitude of the distance change is going to be a over omega squared. So when you're looking at nanohertz versus kilohertz, that is 12 orders of magnitude in frequency, which means a given acceleration, right, a given force would correspond to a 24 orders of magnitude larger displacement at low frequency than it would at high frequency. Is that clear?
Okay.
so that is large part the problem, that at low frequency, you have so much time for an acceleration to build up and cause trouble. The second aspect of this is also a question of how do you build so how does LIGO work, right? LIGO actually builds a filter in some sense, right? So let's think about how LIGO works. The way LIGO works is that you have the ceiling, which is attached to the ground, right? So there's a seismic wave. That seismic wave will cause the ceiling to also shake. But there's a mirror, and you have to basically decouple the mirror from the ceiling. So how do you decouple the mirror from the ceiling? Well, you attach a spring, right? And ultimately, all these things are really, they're just doing some, I mean, so this is now some kind of a resonator, right? So this is a resonator because I have a spring attached to a mirror. So that's like an oscillator, right? So this is an oscillator. Think of this as an oscillator. As an oscillator at frequency omega, which is equal to the square root of k over m, right? K is the spring constant, and this is the mass m. So we know what happens for let's now subject this oscillator to a variety of noise sources, okay? So let's say there's a force, F naught e to the I omega naught t, okay, acting on this oscillator. We know how this oscillator responds. The response is basically going to be equal to delta x, which basically will go as F naught over m, some amplitude, divided by 1 over omega naught squared minus omega squared, right? Some kind of resonant response like this. That's basically how it's going to scale, right? Now, the key point is the following. The omega naught, right? That is the frequency of the noise. I don't control that. It is whatever the world gives you. Omega is the frequency that I'm able to build, okay? So now comes the challenge, right? I have two things. One is I have to suppress the noise. At the same time, I don't want to suppress a signal, right? We need to suppress noise, maintain signal. If you also suppress the signal at the same level, there's no point. Okay. So let's now say that I have a gravitational wave of a certain frequency omega that I'm trying to see. Okay. What that means is that it better be the case that the spring constant here, or rather the fundamental frequency of the system. So yeah, so let's put in some notation, right? I'm trying to see a gravitational wave, let's say of frequency capital omega. That's what I want to see. The gravity wave is at this frequency capital omega. So the gravity wave also will appear in as effectively some kind of force on the system. You can think of it that way. So what you want is you want the response of the gravitational wave to be unsuppressed in the system, right? That means if you look at how the system is responding, it has to be the case that the frequency of the oscillator better be less than the frequency of the gravity wave. Because if the frequency of the oscillator is greater than the frequency of the gravity wave, the response will be suppressed as per this formula, right? I would just simply replace omega naught by capital omega because that's a forcing term here. So in order to maintain the signal, I need small omega, which is the frequency of the resonator, to be less than the frequency of the gravity wave I'm trying to see. At the same time, to suppress the noise, whatever noise I'm worried about, it better be the case that the frequency of the noise is less than the frequency of the oscillator. That's what I require, right? So now think about this fact that if I'm trying to create a kilohertz gravity wave, which is what LIGO is trying to do, it turns out that you can go and look at various spring constants that humanity is able to make, and you're able to satisfy these conditions. That's why LIGO is successful. Well, if you try to go and detect gravity waves at a frequency of a nanohertz, first of all, if you try to build a resonator, you will fail because human beings can only make certain kinds of frequencies with our springs, right? Because the spring constant is determined by various material properties. So even this particular aspect becomes extremely difficult to satisfy. You're not able to hang the object from something with a spring constant that will be lower than the gravitational wave period. So that's a fundamental reason why you can't really create vibration isolation at low frequency. As you go to lower and lower frequency, and by low frequency, I mean below maybe 10 hertz, it becomes very, very difficult to actually create such vibration isolation systems. So it is really a couple of issues. One is that ultimately I'm trying to prevent an acceleration from giving rise to a large length change, and at low frequency that gets more and more complicated because of this 1/2 AT squared. The more time I have, a given acceleration corresponds to a much larger length change. At the same time, it is also the case that the spring constant of the system is something that I cannot control that easily. So at low frequency, it becomes much, much more difficult to create vibration isolation in general.
And the statement is that this atom interferometer, doesn't have this problem because it's in free fall.
It's in free fall, exactly. Okay.
Yeah. But at some level, there should be some kind of frequencies that it will be sensitive to, right?
Yeah, so the atom interferometer, the sensitivity, so you can ask, how do I get this 0.1 hertz to 10 hertz, right? That's what I said I'm maximally good at. It's actually for a couple of reasons. So one of them is actually fairly fundamental. So the idea that we had terrestrially, okay, so it's not a space experiment. Terrestrially, the idea we were having is to say that I'm going to have this kilometer-long mine shaft, and I drop these atoms at the top and the bottom, and I'm going to measure the distance between them. That was kind of the cartoon idea that we kind of talked about. So one can ask, what is the problem at low frequency, right? Why can't I do, because I've essentially eliminated vibration noise by dropping it. So why can't I go to extremely low frequencies? Why do I say 0.1 hertz to 10 hertz? The problem is something extremely interesting, which is that, remember the seismic noise, right? And I said, yeah, it is in fact true that when the world shakes, because the atoms are in free fall, the seismic activity does not directly couple to them, right? Seismic activity does not directly act on freely falling atoms because the atoms are in free fall. However, I can't shield the atoms from gravity. So when I have this seismic wave happening, the seismic wave will gravitationally, through Newtonian gravity, act on these two atoms, right? I can't do anything about it. I can't shield it. So it turns out that at frequencies below 0.1 hertz, the world shakes so much that even the gravitational effects, okay, of this seismic noise on the atoms are so big that you cannot see gravitational waves of interest. So this is a famous point by Peter Salson. Okay, I think he figured this out in the 1980s, right? That at frequencies below something like 0.1 hertz, or maybe it's 0.5 hertz, something of that order. So let me make it approximate, something like this. The gravitational effects of seismic noise are too high. Okay, so which is why even if you build the world's best vibration isolation system like we have, since you cannot shield gravity, anything below 0.1 hertz on the ground terrestrially, you cannot do anything, which is why you have to pretty much go to space for this kind of idea.
Sorry, I'm trying to understand the statement. So for example, does this mean that, let's say if I measure acceleration due to gravity at a particular point, let's say where I'm sitting, and there is like a noise in that acceleration due to gravity of this frequency, is that?
Yes.
Of an appreciable amplitude.
Yeah, appreciable compared to gravity waves, what you're trying to see, of course.
Yeah, appreciable.
Right?
So
yeah, that's right.
Oh, okay.
Yeah, so like at the level of something like 10 to the negative 13 times the acceleration, so something like an acceleration of the order 10 to the negative 12 meter per second squared, right? So that's what we would need in order to see gravity waves. And at this level, okay, if you go to like 0.1 hertz, you're going to find that the shaking of the earth and actually even the atmosphere. So there's weather, right? So the main point is that when you're going down to, frequency of around 0.1 hertz, right? That corresponds to a time scale of around 10 seconds. And turns out that the world shakes enough over every 10 seconds. There's like mild changes in the weather also at these frequencies, which actually correspond to enough of a movement of mass that the gravitational effects are at this level, 10 to the minus 12 meter per second squared. So of course, many orders of magnitude smaller than little g, like little g is 10 meter per second squared, but still it's big enough for gravitational wave detectors. So you may actually even know that LIGO, for example, is able to see the fact that when the waves of the ocean hit the continent, right, the continent jitters. So LIGO can see those things gravitationally.
So this 0.1 hertz statement is like people have measured it, or is this an estimate?
Yes, it's measured because you can just put a seismometer on the ground, and the seismometer simply tells you how high these waves are going to be. Right, so you can literally just put a little thing on the ground, and you say, oh, this is how much the ground is shaking. So that is easy to measure, right? So that's a direct measurement of length. So once you have measured that length, you know the ambient density of the ground around you. And from that, you can calculate what this should be. So nobody's actually literally measured this because nobody's really gotten a, well, in a sense, if you want to know the gravitational effect, you require a gravitational wave detector operating. But you don't need to do the gravitational measurement. You can just directly measure how much the world is shaking and then use Newton's law to predict what this noise should be.
Right.
Same with weather too. Like we have weather stations, and the weather stations measure changes in pressure at various points on the ground, and you can do that as a function of time. And then you can say, well, this is how much the air density is. Let me make a prediction for what the gravitational effect should be.
So maybe, like I'm asking a very naive question. So how do like things like, atomic clocks work, in the sense that they still seem to keep times, right?
Yes. So there are a couple of issues. One, of course, is that a typical atomic clock is not requiring the same level of precision that is being demanded here. Okay. And also the key point is that, we are looking, so this is a question of the wavelength of the gravity wave as well, right? So, so this is an unfortunate coincidence of scales, it turns out. So, any gravitational effect, as you're well aware, can only be seen like it's sort of tidal, right? In a sense that essentially what I'm really doing in this experiment is that I'm comparing the acceleration due to gravity here, G1, with the acceleration due to gravity here, right? So I'm doing G1 minus G2. That's what I'm measuring, right? I'm doing a comparison between these two things. And it turns out that if I look at the actual tidal, so it's a tidal effect, right? It's G1 minus G2. So it turns out that the wavelength of the seismic waves corresponding to 0.1 hertz, their wavelength is order 1 kilometer as well. That's just a fact about the world in terms of the sound speed, things of that kind. So if you take two objects and you separate them by about 1 kilometer, of course, the difference between these two guys will be of that order. I mean, that tidal effect is basically unsuppressed. But the closer you bring these two guys together, of course, that effect goes away. The tidal effect goes away, but so does the gravitational wave effect also, right? So that is why for gravitational waves, the fact that these things are very far away doesn't really, in some sense, do anything about it. But for your typical atomic clock, that's not what you're doing. In a typical atomic clock, you're not actually comparing two atomic clouds at two different distances. You just have a single clock that you're just building in a given location. And essentially what you're doing is, first of all, you're demanding much less precision. You're not actually requiring the precision of a gravitational wave detector. You're requiring something like several orders of magnitude less. Okay, so that is why these effects don't really become that problematic for them just yet.
Like, for example, if I had like, like a much larger shaft, I don't know how practical it is, like say
Mhm.
10 kilometers or something,
Yes.
it would be better, you
That
say.
would be better, yes. So in fact, there's an experiment called Einstein telescope that some people would like to build, and they would like to put all of this like a kilometer underground or something, several kilometers underground, I think. Uh, and if you were able to do that, it's just expensive. Then you would of course be more shielded from the surface noise, precisely for the reason that you mentioned, which is the statement that this is now, if it's like 10 kilometers, let's say you're able to do that, you would then be suppressed at some level from this noise by a ratio of distances squared, something like that. So we did in the past think about the possibility of using some of the deep oil shafts. So, there are these guys, the oil wells, some of them go several kilometers deep. Some of the deepest mines in the world are more like, 3 to 4 kilometers underground. So those could be things that one could actually repurpose for this. I believe that the Russians, in the Cold War, people were just doing all kinds of crazy things, right, to prove themselves to be better. I think someone may have even like dug something. This was done for no reason. It was just to prove that they were better diggers than the Americans. I think the Russians went like 5 or 6 kilometers underground. The problem is, as you go deep underground, the earth gets hot very quickly. So remember, the crust of the earth is only like a few tens of kilometers, right? I think maybe only 10 kilometers. So things actually get extremely hot pretty quickly. So you can't do much deeper than that anyway. And it's certainly expensive. So, but I don't know. I mean, like, if you could, the other alternative is to go to space, and maybe going to space is cheaper than digging underground. I don't know. I don't really know the details of some of these political questions. But it is certainly true, right? It's one of those amazing things that we have gone to space relatively often in the last 50, 60 years, but we haven't really dug deep under the ground that much because it's just more complicated. And I mean, for these reasons, that it actually gets hot pretty quickly, things of that kind, that we've probed outer space more than we have probed the depth of the earth.
Okay, thanks.
Sure. Yeah, the students should speak up more. I mean, I'm sure you guys have questions about something, something or the other. Since you can't even see me, I'm sure I'm much less intimidating. So just please feel free to speak up. I mean, it's perfectly okay. Like, I realized you guys come from a different field. You may not have thought about many of these things. So it's just a question of being curious. Speak up. Well, maybe everyone's tired after a couple of weeks of online lectures. Oh, all right. Well, if there's nothing else, we don't have to stick around. I'm happy to sign off.
Yeah, so are there any questions? I mean, maybe if you don't want to speak up, you can also type, in the chat. That's also fine. Okay. Okay, I don't. Okay.
Oh, so there's someone here. Okay, you talk about CMB polarizations used for detecting. Can CMB temperature anisotropy also be used for dark matter detection? Temperature. Well, okay, that's kind of a more of a complicated question. So, let's see. So, by temperature anisotropy, you mean so there are a variety of CMB probes of dark matter. Okay, so it is not necessarily a probe of anisotropy. So let me be a little bit more careful about what I say, right? So yes, there is some sense in which certain kinds of dark matter can be seen by anisotropy. People have written papers about this. So essentially, what you can say is that if there's very, very low mass dark matter, right? Very, very light dark matter, essentially Hubble scale, something like of this kind. And let's say it changes literally the mass of the electron, right? So one can think about it the following way, that here's the CMB far away. And if there is a wave, right? It's a lot like how one uses CMB to detect gravitational waves, right? To some extent. So let's say there is some kind of a wave that actually literally changes the electron mass at different points in the sky. So electron mass, let's say, is a little different here versus a little different here. ME is changing. And if the ME is changing that way, you will indeed find there's a change in the temperature of the CMB here versus here, because at the end of the day, all of these things are tied to some kind of atomic scale. So you could indeed do that. That is a possibility. I personally haven't studied that topic in the sense that, with things like anisotropy, there's just a limit, right? In a sense, we've measured what it is. So it is difficult to see how you do better than what you have already probed. So I don't know if there's an active experiment looking for it, as opposed to saying there's a limit on these things. People do use the CMB for a variety of dark matter probes, though. So for example, if the dark matter was annihilating or decaying, things of that kind. So you can do the kind of process like this. You can say dark matter comes, and let's say it becomes electrons, E plus E minus, things of this kind. So all of these things will deposit energy in the early CMB. And when it deposits energy, it can actually change the thermal properties of the cosmic microwave background, right? So this changes the thermal properties of the CMB. So specifically, it can actually make it deviate away from the Maxwell distribution. You get what are called mu distortions and all kinds of distortions. So people do use studies of the thermal nature of the cosmic microwave background as a way to understand if there was energy being dumped in the CMB at the time of the CMB itself. So there's an instrument called FIRIS, which was flown, I think, in part of Kobe in the early 90s. And they are the best measurement of the thermal nature of the CMB in many ways. But people have subsequently used things like WMAP, etc., as well, to probe all kinds of spectral distortions, try to see if the CMB is really a thermal spectrum or not. And that is, in fact, a constraint for several models of dark matter, which would deposit energy in the CMB. So it's not perhaps exactly a use of the temperature anisotropy per se, but it is definitely using the CMB to probe these things.
Okay, are there any other questions?
Yeah, I mean, just speak up instead of typing, it's a lot easier.
Okay. Okay.
Great.
Yeah, I don't see any other questions. So then let us thank Surjeet, and since this is also the last tutorial, and I'd also like to thank all of you for coming. For 2 weeks, this online thing is pretty, not optimal, but still, I think it has been a very good experience. So thanks everyone, and thanks Surjeet for taking.
Thank you. Good luck to all of you.
Yeah.
Take care.
See you at ICTS at some better times. So
I hope so. Yeah.
okay, and same goes for everybody also. I hope all of you could come at some point. Okay, so see everybody, and thanks for everybody on the ICTS side. The IT team and the programs office and so on. So I guess Aninda had already said his thanks on the Friday, and this is thanks from my side. Okay, so thank you everyone, and keep safe. See you. Bye.
Bye.